This is a recording of a live webinar filmed on September 11th, 2024, the first in our three-part series entitled Expert Insights Food Safety. Join us for the two remaining live events on September 18th and 25th, covering food-grade lubricants and defoamers. Click the link in the description to learn more, or to follow us on LinkedIn to be kept in the loop of upcoming events.
Hello, everyone. Good afternoon. Thank you so much for joining us today. For everyone who doesn't know, this is the first segment in our food and beverage webinar series that we are hosting for the month of September. These presentations are being given in order to provide insight, knowledge, and familiarity across the DuBois line and share some of our experts' knowledge across the board. My name is Carmen Seibert, and I will be the host for today and the next two calls that follow in the coming weeks. I am the product line manager for food and beverage here at DuBois, and I've been with the company for just over 2 years now. We've got some really great information for you all today. We will be going over CIP cleaning and practices, and also the ins and outs of open plant cleaning. Our two experts, John Mulhern and Keith Seyfried, will be giving these presentations respectively. I do want to say that if any questions come up at any point during the presentation, please direct those to the Q&A tab so we can address them at the end with the allotted time. First up, we will have John Mulhern, who will be going over CIP cleaning and practices. John has been with DuBois for over a year now, but has over 35 years of experience in food processing, technical sales, and business management. John is a fountain of knowledge when it comes to food, beverage, and brewery, pharma, and even dairy. Currently, he is the technical specialist for food and beverage here at DuBois. But with all that being said, I will now pass it over to him to take it away.
Carmen, thank you. And thank you everyone for joining this afternoon. I'm very excited to be able to present to you all. In terms of the presentation on CIP fundamentals, in the time allotted here, approximately 35 to 40 minutes, we're going to take somewhat of a 10,000 foot view, but we will cover, I think, what I believe are critical CIP fundamentals. And it's worth mentioning that in the context of the food industry, there are an abundance of resources that we work with, and certainly our customers work with, in terms of process equipment and design companies, specifically designing CIP systems, including the programming of the systems. There's also colleges such as even Ohio State, Penn State offer typically 1 week training programs specifically on CIP. And having said that, let's jump right into it. So clean in place, why CIP? We'll cover some of the reasons, the advantages of CIP, the performance factors affecting the process, requirements, the components of the systems, different types of CIP systems, and there are many different configurations. And then finally, we'll look at some DuBois product selection options specifically designed for the CIP process. So in terms of a definition, my appreciation to Haskell Engineering, Cyberling Associates, who design and build skidded CIP systems. And this is a definition afforded to me by that group. So when we look at a CIP unit like the one in the picture, you're essentially looking at a skid mounted system. It includes the CIP pump. In this case, it's a single tank. There's heat exchangers, piping, sensors, etc., all on board that skid, and everything is managed right there. So a CIP unit could be defined as the skidded components for delivery of the flush and wash solutions at a controlled flow rate, temperature, and concentration. The system itself then would include distribution lines, for instance, where operators would hook up to divert flow to the appropriate circuit to be cleaned. And then a CIP circuit is a common group of process equipment. It could include lines, silos, tanks, even ovens in some cases. Essentially all the devices that are being cleaned, including the valving system, routing the flow to the various parts of the system. So if we look at the function of a CIP system in a nutshell, we're cleaning and sanitizing the internal surfaces of food processing equipment for the most part without disassembly or manual intervention. So we're talking about tanks, kettles, ovens, silos, line circuits, including, it could be several hundred feet or thousands of feet of process line, plate heat exchangers, tubular heat exchangers, evaporators, dryers. All these lend themselves to cleaning in place. And the goal is to provide a system that allows for a repeatable standard of cleanliness by automating the key cleaning elements. So we're trying to take the human aspect out of it and ensuring consistent, repeatable sanitation results each and every time. And basically the key elements we're controlling is the cleaning time, the action or mechanical flow rate, the chemical and its concentration used, whether it's a detergent or sanitizer, and then the actual cleaning temperature. So the main advantages of CIP are time savings over manual methods. We get consistent, repeatable results. Just to repeat that, time savings is a big one, just based on the automation and the ease of connecting up cleaning circuits, at least typically the automated cleaning circuits. And then the ability to log or data log and record the cleaning parameters, which is of immense value to internal quality assurance groups, as well as third-party auditors, whether it be BRC, SQF, etc., when they want to validate and verify that cleaning is actually accomplished per the SSOP or the standard operating procedures at the facility. Critical point I mentioned earlier, CIP is basically cleaning in place without disassembly. That said, there are components typically in circuits that cannot be CIP cleaned. Usually we're referring to threaded fittings, sample cocks on silos, tanks, storage vessels, door gaskets, areas in equipment with blind spots, for example, an excessively long dead leg. You may have agitator blades and shafts that need to be removed because they are not fitted or 3A rated to be cleaned in place. And with that in mind, the 3A standard for sanitary design is recommended. It's basically an assurance that the system is designed to be cleaned in place. So it's something you would look for when selecting any new processing equipment, or even if you're evaluating existing equipment, to easily determine if it is allowed to be cleaned in place. If they are not sanitary or the CIP flow cannot reach them, then the parts must be disassembled and cleaned out of place manually, such as using a bucket and brush, or very commonly in a clean out of place tank or COP tank. So the performance factors affecting CIP, pretty much typical of all the factors affecting any type of cleaning, whether it's manual or the open plan cleaning that Keith will cover subsequently. Tact wins. So tact, we're talking about time, cleaning time, the action or flow rate, the chemical, detergent and its concentration, and the temperature used for cleaning. So typically you can interchange these a little bit. If your temperature is lower than desirable, you can compensate by increasing chemical concentration. Similarly, if your flow rate's a little lower than usual, you may also increase chemical concentration and time. And then you become more dependent on a soaking action as opposed to the mechanical scrubbing action afforded by an appropriately designed CIP supply pump. Other factors affecting cleaning that need to be taken into consideration are the water quality. Is it city water? Does it have high hardness levels? Perhaps you have DI water or RO water. All will affect your choice of cleaner. Then individual cleaning considerations such as the design of the specific equipment needs to be taken into account, spray ball design, etc., to make sure you're actually contacting every piece of the equipment. Then the nature of the product, residue or soil. Is it a proteinaceous type soil? Is it a cold storage vessel? Or are there carbonaceous burnt on deposits like you might see in a snack food type situation? And then finally, the surface material or the substrate. Typically, we're in a food plant, we're most commonly going to see 304 series stainless steel or 316 series, occasionally 400 series stainless steel for used in grinders and the like, where the material can handle the grinding effect more effectively than the other grades. But it's not beyond the realm of possibility for us to see soft metals, maybe aluminum, copper, brass, sometimes in a circuit. And this will drastically affect our choice of detergent because we obviously do not want to corrode or attack equipment that is subject to attack by a conventional high alkaline or high acid detergent. CIP needs velocity, so the mechanical action basically in a CIP system is provided by the CIP supply or delivery pump. The well-established rule of thumb over the years, and it's used in dairy design, which is one of the more sensitive processes based on its micro sensitivity. Rule of thumb is we need a minimum of 5 feet per second flow rate. So the bottom section of pipe kind of indicates with the arrows, not alone do we have a full pipe with cleaning solution, but we get a turbulent action, almost like a scrubbing effect. The other two pipes would indicate poor or partial flow, where we're not completely filling the pipe to be clean, so we risk not effectively cleaning that and basically ending up with some potential product contamination when we start up our process. In terms of translating 5 feet per second to different line sizes, a 2-inch line, for instance, will require 43 gallons per minute to achieve that flow rate. If it's a 3-inch process line, we need to be as high as 101 gallons per minute. And then all the way up to a 4-inch line would require as much as 180 gallons per minute to effectively clean that line and achieve your minimum 5 feet per second. We've got a footnote on this slide that in certain instances, if you have specific T designs with sensors or perhaps excessive dead legs or a highly viscous product residue, there are situations where we would prefer to see flow rates of as much as 7 to 13 feet per second. But again, for the norm, I would defer to that 5 feet per second requirement is typically what we need. In terms of cleaning a silo or a tank wall, typically with a spray ball fitted either at the top of the vessel. And nowadays, it's not unusual to see a bottom-up spray ball in some of the larger silos like Feldmeyer or Walker, where the spray ball is actually located in the center of the base of the tank and actually sprays upwards. So we need a minimum of 2 to 2.5 gallons per linear foot per minute, or 0.2 to 0.3 gallons per minute per foot squared of internal surface for a horizontal or rectangular tank. These are not my calculations, but they're well established, and certainly working with an equipment design engineering company, they will factor all this in terms of the spray ball selection specifically designed for the vessel and the equipment to be cleaned. If we're cleaning a plate heat exchanger, at a minimum, we would want the flow to be greater than the processing product flow. And ideally, we would like to see it as high as twice the flow rate when we're in production mode. Again, the goal is turbulent flow, stuffing the system with enough flow to prevent that channeling or laminar flow type effect so that we get a good scrubbing action. In terms of just going over quickly as possible here, some of kind of the principles of CIP engineering, the lingo, the terminology you're going to see relative to CIP. So just like process, you have CIP tanks, including CIP rinse tanks, CIP rinse recovery tanks, a CIP caustic reuse tank, a CIP acid reuse tank. It's going to have automated valving on the system. It will have a supply pump, typically a centrifugal CIP supply pump or delivery pump. It will have a return pump to evacuate vessels being cleaned and return it to the CIP system and create a cleaning or recirculation loop. Occasionally in industry, you may come across an eductor or a vacuum-based system based on a Venturi effect, where we don't have individual CIP return pumps, but rather a motive pump and a separate tank located at the CIP system to pull a vacuum to allow the cleaning solution to be returned in that manner. But they're pretty rare nowadays in my experience, but you may come across them. There will be often an air blow in the system, which typically will blow the rinse water out of the system at the end of the pre-rinse stage to avoid dilution of the subsequent cleaning solution. And likewise, after the cleaning solution has been circulated, we will often air blow that solution back to the reuse tank to recover as much as possible, so we're efficient in both chemical, water, and energy use. Different heating methods for CIP systems. Typically, it's going to be a heat exchanger nowadays. Some older systems, you may see direct steam injection. Chemical is either timed, proportioned into the system, and very often, and most commonly now, I would say conductivity controlled. And in terms of controlling everything or the brains of a CIP system, it's typically a programmable logic controller or PLC. And this basically accomplishes everything from opening the correct valve, operating the pumps, water valves at the appropriate times, making sure the system steps through and meets all the program parameters, including flow rate, temperature, time at temperature, etc. And it'll often also now incorporate CIP monitoring equipment such as conductivity, and may graphically data log that system for review later on so that it can be pulled up, reviewed for audit purposes or troubleshooting. So basically, when we're CIPing a circuit of any description, lines, tanks, etc., the CIP unit itself acts as the storage or makeup system for the CIP solution. So everything is controlled at that unit. As you saw in the initial picture on the skid, we control the detergent or chemical concentration and the temperature. The CIP delivery pump or supply pump very often nowadays will have a variable frequency drive. So that will be programmed based on a signal from a flow meter to deliver the exact flow rate required for a specific line or a tank and a specific spray ball design. The CIP delivery pressure and flow rate are specific to every item you're cleaning. So a large pipe needs more energy than a small pipe. And as I mentioned earlier, if we're achieving 5 feet per second in a 2-inch line, we need minimum 43 gallons per minute. If that's a 3-inch line, we need 101 gallons per minute. Likewise, larger tanks have much larger surface area. They're going to need more energy, heating time, etc. Obviously. And all that has to be taken into account in determining the optimum time at temperature programmed into the system. A critical aspect of CIP is what I like to refer to as hydraulic balance. So in other words, if I'm cleaning a tank, I would prefer to see that tank or vessel or silo dry bottom. So in other words, the CIP return pump is evacuating that vessel as quickly as the CIP solution is received into the vessel via the spray ball. This prevents pooling of water, detergent solution, maybe creating a bathtub type ring effect on the tank and risking incomplete cleaning. And it also allows the cleaning solution to impact 100% of the surface of that vessel. Where you see systems that are hydraulically imbalanced, let's say the CIP supply pump is exceeding the rate at which the return pump can return the cleaning solution, often the systems may start to add additional water to compensate, to maintain flow, which means more water, more energy. For conductivity controlling the solution, we'll add more chemistry. We'll need more steam to heat that added water. So hydraulic balance to me is probably one of the more critical aspects of an effective and efficient CIP system. On the bottom here, referred to a liquid ring pump, and actually we'll get to that on a future slide. It's basically another option for CIP return versus a conventional centrifugal pump. When it comes to valves, you're going to see multiple types: divert valves, shut-off valves, mix-proof valves. Again, mix-proof valves have been approved by the FDA now in the US for several years. They were in Europe for many years before that. They're also referred to as smart valves, in that they have the ability, if, for instance, the system, the PLC, detects that the valve was actuated, but it doesn't detect via a contact switch or otherwise that the valve actually activated, it will alarm the system, notify the operator, typically via the HMI screen or interface, and actually put the system on hold or shut the system down. Huge advantage of mix-proof valves. You know, in the past, you might often have to wait till all production was completed before you could begin CIP. Mix-proof valves allow you to actually have cleaning solution safely on one side of a valve and processed material or food material on the other side without any potential for mixing. So as we see more and more automated facilities, I see more and more of this type of valve at our customers. The CIP supply pump themselves in the picture, it's a 2.5 inch by 2 inch supply inlet and outlet. It's typically a centrifugal design. This allows one to deadhead the pump. So for instance, if we elect to close a valve or a valve shuts against the CIP flow, it doesn't negatively affect the pump. Typically, you're going to see these pumps rated for anywhere from 80 to 200 gallon per minute flow rate at 60 to 100 PSI. Typical motors are operated at 3,500 RPM and in ranges from 5 to 20 horsepower. And, you know, referring back to 3A standards, the pump must be 3A approved to be designated as effective and approved for CIP purposes. As an example of a CIP pump curve, so basically a pump supplier or your equipment supplier designer, when they're looking at your tank or silo or line based on, you know, numerous valves, different head pressure depending on how high the lines go, etc., the size of the line, the diameter of the line. This curve allows them to establish the optimum horsepower for the pump to make sure we achieve the minimum flow rates. Typically not something I would be doing, you would be doing, but just be aware that this is how pumps are chosen. There is an optimum size pump for every application. Likewise, CIP return pumps, they will typically, on average, match your CIP flow rate, or hopefully be even able to exceed that flow rate at 80 to 200 gallons per minute. You typically see the motors and the RPMs will be lower, and this is because on the return, you're typically just returning directly to the CIP unit, and you don't have all the valving and head to overcome that you do on the CIP supplies. So that's why they're typically going to be a smaller and cheaper pump. They need to be sanitary design, again, 3A rated. And next slide. So if we're using a process pump for CIP return, such as the one in the picture, they typically need to be fitted with an air eliminator. And an air eliminator essentially allows the entrapped air in hot detergent solutions to be evacuated and avoid cavitating the pump. So you basically have efficient return flow throughout the CIP program. They're typically installed just above the top of the return pump per the installation in the picture. Just following up on the air eliminator, the working principle is basically it's a double-seated valve with a freely moving plastic ball. And the ball, which is lighter than water, closes against the upper or lower seat depending on the pressure conditions, and effectively allows you to eliminate air from the system and basically maintain efficient CIP return flow for the duration of the cycle. Mention liquid ring vacuum pumps. This is a different style pump. It has the advantage of not requiring a flooded suction, as is the case for centrifugal pumps. It's a unique design. You get very linear pump curves. It's extremely efficient, even in situations where piping isn't optimally designed or pitched. It will effectively keep a tank, even if it's almost sucking the solution uphill, it will keep it effectively evacuated based on its the pump's ability to essentially create a vacuum. Some might cite disadvantages in terms of cost or maintenance, but I would say based on the efficiencies a pump like this can bring in terms of maybe shorter cleaning times, less water, chemical, and energy, I would look at the ROI for an investment in a pump like that on that basis. And next slide. Okay, so in terms of CIP heating methods, typically it's going to be a heat exchanger. You may also see a steam inductor like the one in the picture. Disadvantage of direct steam injection is, you have the potential to introduce boiler feed chemicals into the CIP solution. And it's also inefficient in terms of water and energy use because you don't get the advantage of returning the condensate back to your boiler for reuse, including the energy associated with the condensate. So not very often seen on newer installations. This is your more typical tubular heat exchanger that you will see. Very often there will be a stainless steel design. Enerquip is a model I frequently see preferred by many of the process equipment design companies. It typically it'll heat all CIP solutions. It can preheat if necessary in advance of the CIP circuit in the case of a reuse system. And typically you're going to see the temperature increase come up incrementally in 10 to 30 degrees Fahrenheit increments per pass. The advantage of heating like this versus direct steam, which can sometimes exceed the temperature required, you won't stress the vessel you're cleaning. It'll be a much more gradual temperature increase. So if you look at some of these larger 50,000 gallon silos, you know, those are relatively thin walled, and it's not too difficult to heat stress the metal. So another advantage of a tubular heat exchanger. And again, we get the extra benefit of returning the condensate to the boiler, getting to, you know, reuse that energy and water. Chemical feed systems they're going to be many and varied in terms of pumps. There's a simple air-operated double diaphragm pump in the bottom left. That's a simple flow jet model. Conductivity are typically inductive probes. So you'll have a display such as the one there demonstrated with a conductivity controller. And the simple schematic basically shows alkaline and sanitizer injection into a single tank CIP system. CIP controls the brains of the CIP system, basically controlling everything that happens in terms of sequencing, the time at temperatures, the amount of chemical added, alarms, holds, etc. Is via a programmable logic controller or PLC. The ones I most commonly see are Allen Bradley, but there are a variety of PLC systems on the market. They also provide an interface for the operator via the HMI screen to make simple time, temperature, and concentration changes. I would stress that if somebody has access to make programming changes, there should be a password for administrator access, because you risk somebody going in and making arbitrary changes and those changes not being logged or documented. So that's something to avoid. Again, CIP monitoring systems, sometimes in dairies, there is a requirement to monitor both pressure and temperature, and it may be recorded on for instance, a circular recording chart. And nowadays, there's a lot of digital recording, which is data logged and stored. Pressure, I would comment, is not a foolproof method of verifying you have proper flow in the system. We would prefer to measure the actual flow rate, typically in gallons per minute. In terms of systems that do have data logging and the ability to store data, sometimes it'll be stored optionally in a graphic form, where you can readily see if set points were made for parameters like supply temperature, return temperature, conductivity, or chemical concentration. And this is especially valuable, again, when you're reviewing the SOPs or even troubleshooting in the event of an issue or a quality problem or otherwise. This is an example of an HMI display. This may basically, the operator basically this would be a touch screen. The operator can see the vessel, the CIP vessel, the level of cleaning solution in the vessel in this case. You can see a couple of green activated valves, which tells the operator the route in which the flow is going. In this case, it's going through a heat exchanger out to a kettle. You can't really see it on the screen, but it'll also display flow rate, return temperature, supply temperature, pressure. This is an invaluable tool in modern systems for an operator to be readily able to determine what's going on in the system and to make sure that it's working normally. Some older systems, you will not have this luxury. You may have a simple interface for starting and stopping with minimal feedback. Given the capacity of modern systems software, I would encourage anybody, if choosing a new system or even retrofitting an old system, to consider this type of design. Okay, different types of CIP systems. These are just schematics. This is a single-use CIP system. Again, single tank, CIP supply pump, chemical injection, or sensors for recording temperature. Next option would be a detergent reuse CIP. So in this case, we would have two tanks. So the rinse tank for pre and post rinses, and then a detergent tank where we actually recover the CIP solution after each wash and reuse it. Obviously, this cuts down on water, energy, and chemical use. We want to realize even further water and energy savings. We might add a rinse recovery tank. So now we're up to a 3-tank system. So not alone are we reusing the wash solution, but we're also reusing the post-rinse wash solution for pre-rinsing. So we get some energy value out of that. We obviously get water savings, and we can basically save on utilities. Next option would be a system where we would add an acid tank. So specific processes where we may be heating products that contain minerals or otherwise that require an acid subsequent to the alkaline wash, we might have an acid tank included in such a system. And again, we would typically, these might be reused depending on your sensitivity to microcontamination, or you might have concerns about allergens where you, in that case, you might default back to a single-use unit. This is a simple graphic demonstrating the washing of a Mueller tank. Very simple in terms of, you see the flow starts out with pre-rinse, and we do a caustic wash. We do a post-rinse or caustic rinse. Then we follow that with an acid. And then finally we do another post-rinse, and that would typically be followed by step 6, a sanitizer. I say this is simplified because I liken this to Robin Williams' description of Scottish golf when he is asked if a golf course is essentially like a bowling alley, and his answer is hell no. You basically have a nice tee box and a green, and you punch a whole bunch of crap in the way, including bunkers and water and bushes and the like. So when you think of a CIP system, beyond this simplified version, remember you've got all the valving, pumps, sensors, and all of those, just like your process, need to be calibrated, checked, maintained on master sanitation schedules, and as well as preventative maintenance schedules. Spray devices, we mentioned earlier in terms of tanks, typically you're going to see static spray balls appropriately drilled and designed to give you the necessary flow rate for the tank you're cleaning. Again, this is all factored in by the engineering design companies when they're fitting spray balls to new or even used equipment. Less common, I would say, are the rotary head type spray balls, which typically clean with high pressure impingement. I tend to see these in reactors or tanks that have maybe very high levels of viscous material burn on, and they need high pressure impingement to assist in the cleaning process beyond just the chemistry. So multiple system options. Again, you see the massive stainless steel compact designs. The CIP in the system is a single-use recirculated system. You see the skid with the pump and all the sensors on board. This basically speaks, this picture of a valve cluster on the floor is an installation in progress. But this is a system that incorporates multiple tanks, caustic, acid, and you can see by the number of valves on the floor, there's probably 50 plus valves, the number of different circuits that are going to be cleaned using these multiple CIP systems. So they can be quite complex and obviously need high degrees of automation and the associated expertise to program such a system. You'll commonly see manual hookups for our central hookup station when the operator sets the system up for cleaning. So the elbows in the picture will typically divert the CIP flow from the CIP supply pump to the appropriate port that may be representing a line circuit and all the different vessels such as silos 1, 2, 3, tanks 1, 2, 3, 4, 5, etc. Newer designs, you'll see less manual connections, such as on this hookup station, and more automated valving. So the operator will have to make maybe just one connection, and then the CIP system, PLC itself, will open and close the appropriate valves based on the particular circuit selected. So again, this is becoming more common, eliminating labor, delays, offering time savings and efficiency, and less potential for human error. Okay, so in terms of just some pictures, we'll quickly review. You see a CIP supply pump in the picture. Often these are controlled. They control the flow using a variable frequency drive. Sometimes it'll actually be a CIP flow control valve instead, which throttles open and closed to deliver the flow rate required based on a signal from a flow meter. This is more mechanical action, and personally, I prefer a VFD drive as a more efficient means with less maintenance. This is a picture of a vertically mounted heat exchanger. Most frequently, I will typically see these in a horizontal mode, but this particular picture, we see the vertical version. Chemical feed systems, as I mentioned earlier, there are many and varied types of air-operated double diaphragm chemical pumps. We've got Wilden, Yamada. In the middle, you see some electric diaphragm pumps, LMI style pumps. On the left, the pumps would be housed in cabinets. Cabinets offer an extra level of safety, and I would encourage same so that in the event of a leak, operators are not at risk due to a leaking fitting or otherwise. And then the various instrumentation on a CIP systems, temperature recorders, flow sensors, pressure sensors, and conductivity devices. In the picture, you see an example of a pressure sensor and an RTD or temperature sensor. So when it comes to selecting a CIP, disadvantages and advantages of the different types, generally speaking, single use, single tank, it's a smaller footprint, lower initial capital cost. It's going to be higher detergent use because you're making up a fresh solution each time. It does reduce cross-contamination risk because it's a fresh cleaning solution each and every cycle versus reusing the previous solution. So, disadvantages potentially are higher running costs, longer heat up times, more detergent use, higher water use, higher effluent generation. I would stipulate, though, that with effective programming, you can make a single-use system extremely water efficient. And then reuse systems, conversely, lower running costs, less water consumption, less energy use typically. You do have the potential as a disadvantage for cross-contamination. Rinse recovery, again, is a good option for reducing water and energy use, adds to the higher capital cost and the footprint of the equipment. A utility tank, I rarely see these, but if a plant is, for instance, in expansion mode and regularly passivating equipment or whatever, they might have a dedicated tank incorporated into the CIP skid to allow this to be used each and every time you either passivate a new piece of equipment, for example, or you want to repassivate an existing piece of equipment. We like to use CIP validation checklists This would be a detailed checklist that we would use in supporting customers to verify or validate that their systems are operating correctly. And the checklist would include everything from operator training, a review of the SSOP to make it sure it's current, that the tanks are clean, the chemical dispensing systems are not leaking, and there are no valve leaks on the system. It would include a visual inspection of the equipment being cleaned to ensure that it's effectively cleaned. We would also verify that components that are not CIP cleanable, that need to be manually disassembled, such as gaskets, spigots, etc., that's accomplished effectively and cleaned and manually cleaned and sanitized. So DuBois, in terms of product options, we are very fortunate as a company. I can honestly say that we probably have a product for any conceivable CIP situation. The goal in using CIP products or products that are designed for CIP is they're typically non-foaming, low foaming, or at best moderately foaming. Suitable for long piping runs. You know, in the picture you see literally miles of pipe and a homogenizer there in the forefront. And ultimately, when we choose a CIP cleaner, we're looking for efficient tank cleaning and sanitizing. So our DuBois product options on the alkaline cleaning front, we would look for low foaming alkaline cleaners in the case of burnt on soils, such as in kettles, heat exchangers, HTSTs, evaporator dryers. CIP HD would be our very effective workhorse. If it comes to a proteinaceous type soil on maybe a cold storage vessel or beverage soils, chlorinated alkaline CIP cleaners are often preferred, such as Kel-Alk CIP. For brewery applications, we have specially built products such as Alcadet. This typically helps us minimize the degree to which acid washing is necessary, and especially if we couple it with an additive such as Kel Brew-Add to minimize beer stone residual or deposition. Another very effective cleaner for a specialty cleaner is our Divopak T. Specifically for beverage and citrus and tea staining, it's uniquely effective in removing such stains and product residues. And then for our pharmaceutical and cosmetics customers, we have our DuPharm product line, specifically designed with surfactants and additives with these types of soils and product residues in mind. In terms of acid cleaning options, our Kel Acid CIP is a nitric phos blend, a workhorse, very effective for removing mineral scale, milkstone, beer stone, and also approved per the ASTM method for stainless steel passivation. If we require a cleaner with a high level of surfactancy or high heavy-duty phosphoric acid-based product, DuPharm 31 is really effective for scale and rust removal. And then for customers requiring an organic acid such as citric, which is often used for stainless steel passivation per the ASTM methods, we would use our GF Acid Clean 9011L. And then finally, we have a broad range of sanitizer options. Our Dicasan CIP is an anionic acid sanitizer. Dicaquat is an acid quat. SHS 900 and Liquid Chlor are both sodium hypochlorite based or chlorine based sanitizers. Dicasan PAA is our peroxyacetic acid based sanitizer, and then Reflex is peroxyacetic acid and nitric acid, where there is a potential for some scale buildup, and the nitric acid component helps reduce the potential for same. I would say in terms of broad spectrum and preferred sanitizers, in most facilities nowadays, Dicasan PAA would be the preferred option. It breaks down into natural ingredients, basically water, oxygen, and an extremely mild version of vinegar or acetic acid. Sorry for rushing through this a little bit, but I think that about does it for CIP. And thank you all for your consideration.
Thank you so much, John. That was great information. Just a note, we will be holding off on the questions. I see some have come in, but we'll be holding off on those for now because we're going to be passing it to Keith to finish us up with open plant cleaning. Keith specializes in R&D, product formulation, quality assurance, analytical laboratory testing, and on-site technical and application support. He currently serves as food and beverages in-house chemist, but he has over 26 years of experience in the food and beverage industry in cleaning and sanitation applications, and he has been with DuBois for 11 years. But I will now be handing it over to Keith to begin his presentation.
So why foam clean? Foam cleaning is very effective to clean large areas. Prior to foam cleaning applications, people were cleaning large areas basically manually, bucket and brush, manual scrub, everything in the room. Foam allows you to foam multiple pieces of equipment, floors, walls, ceilings down all at the same time. It's also useful on a wide variety of soils, anything from light to heavier duty soils like you'd find in smokehouses. And it's also easy to identify areas where you've cleaned or where you're in a cleaning process versus areas where you're not cleaning because of that foam and that visual identification. And difficult to access areas, overheads, vertical surfaces, things that would be difficult to really get up there with a bucket or a brush and clean, you can foam and minimize some of that manual scrubbing. So what are some of the key properties of a foam cleaner? As John indicated with CIP, you can alter times and you can alter temperatures. Well, with foam cleaning, you really don't have that flexibility because your time is kind of limited to the amount of contact time the foam hangs on the surfaces, and you don't want to foam clean at elevated temperatures because you don't want rapid drying of the solution. So you're foaming at ambient temperatures. You're trying to maximize your contact times with the foam, and the real key properties are soil emulsification, surface tension reduction, dispersion of the soil. You want to pop the soil off the surface and you don't want to have it redeposit. And you also have to be able to accommodate a wide variety of water hardness conditions throughout the region. So typical compositions of foam cleaners are going to have things like strong alkali, sodium hydroxide, potassium hydroxide. They're very good at displacing soils from the surface. Alkaline builders, silicates and phosphates, to name a few, to provide metal safety or water hardness conditioning or buffered alkalinity. And then chelants, gluconates, polymers, phosphonates, EDTA. These are things that are in these formulations to accommodate the different water hardnesses that you'll encounter. Oxidizers, very good at peptizing proteins and removing soils, with the workhorse being sodium hypochlorite, but you also find hydrogen peroxide based products. And then solvents. Typically the solvents used in foam cleaners are not heavy hydrocarbon solvents. They're aqueous compatible solvents, things that will help to emulsify the greases and oils that you encounter in the food plants. And then acids. You'll have blends of mineral and organic acids, but typically with the mineral acids, you tend to stick more with the phosphorics rather than some of the heavier hydrochlorics or sulfuric acids due to the corrosivity of those materials to stainless steel. And then some of your more prevalent organic acids, things like citric or glycolic or hydroxyacetic acid. And then surfactants. You have to have the surfactants in there. That's what's generating that foam. That's what's giving you your contact time. That's what's helping you reduce that surface tension and helps with the emulsification of the greases and oils. So what's involved in a typical foam cleaning process? I mean, a typical foam cleaning process really falls back to the procedure. It's very important to make sure that you're doing a good job with your dry pickup and pre-rinsing to remove all the gross soils from equipment and environmental areas. This is critical because foam cleaning is designed to remove those residual soils, not so much the gross, heavy incrustation of soil. You'd want to apply the foam, and when you apply foam, you want to apply it from the bottom up. This is going to help with reduction in dry down and streaking. You don't want your surfaces to dry with the cleaner on them, because then you'll redeposit not only the soil that is dispersed in the cleaner, but also the chemical packages associated with the cleaner. And then manual scrub. You know, foam cleaning is not the end all be all of the cleaning. You still need some mechanical action in there. There's sometimes you have tenacious soil deposits that still require a manual scrub. So you don't necessarily get away from manually scrubbing with foam cleaning, but you do reduce the amount of manual scrubbing. And then most foam cleaners are going to say leave on surfaces for 10 to 15 minutes and then rinse. Traditional foam cleaners tend not to last for 10 minutes. It's more in the line of 4 to 7. So what you find is people will reapply foam. So it becomes an application, a reapplication, a manual scrub. We do have some extended contact time cleaners that you can actually apply once and get that full 15 to 20 minutes of contact time before you do a rinse, and we'll discuss those in a later slide. But once you rinse your surfaces, you also want to inspect them. You want to verify that your cleaning process was thorough and complete. So you can inspect those visually. You can use ATP swabs, micro swabbing. But it's very critical to inspect those surfaces after you've done your foam cleaning. And then the application of a final rinse sanitizer. So how's the foam applied? There's a lot of different equipment out there to apply it, and we're going to go through just a few. You know, there's portable foam equipment where it's basically a vessel that you can fill up, either manually dose in chemical to it or fill it up through a dispensing system. And it's self-contained and requires usually just a airline in the area so that you can hook it up. And these can be wheeled from room to room to room. And as long as you have an airline hookup, you don't really need a whole lot of other utility other than that. Then there's wall-mounted foamers, and these are designed to be drops within a room, and they will actually require concentrated chemical to be at the drop so that it can be proportioned into the foam unit and dispensed out through the foaming wand. These will require water and airline hookups. They do make some that only require water. But in general, you find that it's a dual feed of water and air to generate the foam. And then there's also centralized foamers. And centralized foamers kind of are similar to a wall-mounted, except that instead of having chemical jugs at each individual wall mount station, all of that chemical dosing and dispensing is done remotely and then piped to the individual stations so that you're not carrying chemical out into the area. All your chemical is in another location. So just to kind of go through a little bit of the DuBois product line here for foam cleaning. You know, we carry a lot of chlorinated foam cleaners, and chlorinated foam cleaners are kind of the workhorse foam cleaners in food plants. They're very good for cleaning the food equipment and facility walls, floors, ceilings, overheads. And they're also very good at removing staining on things like processed meat cutting boards. We have various options here with our products like Kel-Alk Foam, Master Clean Plus, Master Clean SMS, Master Clean DS, and each one of these are slightly different from each other. When you look at Kel-Alk Foam, that is a very good quality economic product offering. Master Clean Plus would be a premium product, very highly built. Master Clean SMS is a soft metal safe version, chlorinated alkali, and then Master Clean DS is really kind of more of like a belt destainer. It's designed to have a high level of chlorine for that destaining process. Heavy duty non-chlorinated products. Now these would be things that would be used in heavier duty cleaning applications like smoke houses or exhaust hoods and stacks, belts or conveyors that are going through ovens or roasters. They're really kind of designed for heavy carbonized soils. So what you're going to find here is these are typically higher in alkalinity levels than a chlorinated alkali, a little bit better, higher alkalinity and solvency built. Things like our AlkaClean JR and CP405. These would be smokehouse type cleaners, very good on carbonized soil. Super Clean is a higher alkalinity kind of product, but than say a Master Clean Plus, but it's non-chlorinated and it's got some solvency to it. And then Super Clean Gel, which is designed for really heavy carbonized soils and really gives you a good extended contact time. And medium duty foam cleaners. These would be your general purpose cleaners. Your multi-metal safe. They're usually safe on plastic and painted surfaces, but they tend to be very effective degreasers. So they have a degree of solvency to them. So Kel No Chlor foam would be our quality economic product, good general purpose solvated cleaner. Our Trio line is our design for the environment. So very good cleaning performance, but with environmentally preferred ingredients. DuFarm LC degreaser. This is a product that's really was kind of geared more towards the pharmaceutical industry, where you have a lot of those heavy oils and greases in the cosmetics industry. So it's got a high degree of solvency. And C1102, which is a very good blend of alkalinity and solvency, encompasses and will remove a wide variety of soil loads. And then foaming acids. When you think about acids and foaming, you're really looking at descaling applications and removal of mineral film, equipment brightening. These products tend to be phosphoric acid or organic acid or blends. That's where these products fall in line, like with our Kel Acid Foam and AC100 and Red Acid Cleaner. These would be phosphoric acid or phosphoric acid organic acid blends. Good foam profile, good cling time. Now, extended contact time cleaners, and I alluded to this earlier. You know, these are going to have longer dwell times. These extended contact time cleaners are kind of a hybrid between a gel and a foam. They don't look like a gel. They don't look like a foam when applied, but they can be applied through your normal everyday foaming equipment. So no specialized equipment needed. They allow you to have those longer contact times so that you're not reapplying chemistry. They also have the extra added benefit of improved rinsability. So when you rinse a foam cleaner, you are a lot of times chasing foam down the drain because there's enough agitation in that rinse water to generate a little bit of foam. Well, the foam on the Exticon and these extended contact time cleaners will collapse in on itself, and you're saving that water. You're not chasing as much foam to drain. So you're picking up that water conservation, and you're also picking up that time efficiency because you're no longer reapplying over and over on the same areas. In that product offering, we have things like Exticon GP, which is a chlorinated alkaline general purpose cleaner. Exticon SMS, that's a soft metal safe version. Render SBG falls kind of into that heavier duty alkaline. product line, but it does give you that extended contact and improved rinsability. PowerLift EX is general purpose kind of solvated degreaser. And then the Super Clean Gel, again, specialty product designed for heavy carbonized soil. And it is kind of the anomaly here from the standpoint of it still has that great cling time and still has good rinsing, but when it is applied, it does look more like a traditional foam than the other four that I listed above.
Well, I think that about wraps it up for Keith and John's presentations. Keith and John, thank you so much for going over all that information. Like I said, some really great stuff here. I know we are a bit over on time, so I'm trying to be conscious of everyone's schedules here, but also wanting to get through these 3 questions that are in our Q&A. I'll take the first one. We have a submission here that says, am I able to get a certificate for participating in this webinar? Yes, you are. Please send your inquiries or your want for a certificate to our marketing email. You can contact them and they will be able to provide that for you. The next question comes in and it is probably more geared towards John and Keith, either of you want to take it. And they state that, is it possible to manually control a CIP process?
I'll go ahead and take it, Carmen. I would say the answer is yes, but depending on the complexity of the equipment or the circuit you're cleaning, you need a very proficient operator. And I think that is one of the challenges in a food plant. You know, if you're running a 24/7 operation and you absolutely need repeatability and consistency for sanitation and food safety, it is possible, but you're going to have somebody recording, especially in the context of third-party auditing today, doing a lot of manual recording in addition to controlling all the manual functions, typically controlled by a PLC controller.
Awesome. Thank you, John. And then our last question for today is, what are the key considerations in planning a CIP installation?
I guess it's CIP. I'll go, Carmen. I would say the key considerations are really to involve all the stakeholders, especially when planning a system, and that involves everybody from operations, quality, obviously, but EHS. CIP systems, have the potential to save or waste tremendous amounts of water, energy, utilities in general. It's really important if you have a sustainability program to take advantage of efficient and effective programming. You can actually document your positive effect on the environment by controlling the various parameters, including water use and energy use. But I would say the biggest oversight I see in terms of CIP is probably overlooking the importance of compliance relative to wastewater permitting initially. Often after the equipment arrives on site and it's being commissioned, people ask the question as to, where are we at with permitting? And similarly with chemical storage, dispensing equipment. I would involve vendors, your expert cleaning and design equipment companies very early on in the process with all key plant personnel. And I would say meet early and often.
Got it. Thank you, John. I think that concludes all the questions that came in for today, but for anyone that's listening in and you think of something after the fact, we do have John and Keith's information up on the screen. So if you would like to message them by email at any point, please feel free to do so. But that will conclude our first webinar for the month of September. Thank you all for joining in and, spending the time with us today to go over some of this really awesome information. If you're interested, next week at exactly this time, we're going to be going over lubricants with Dave Darling. There's a bit of a preview on the screen there as well. So hope to see you all there. Once again, thank you again for all the time and consideration, and I hope you all have a great rest of the day and rest of your week.